So we're doing Kolmogorov complexity in this last two lectures. And so let's dive in. So there's a nice story here from Wolfgang, I guess, that so what is the idea of Kolmogorov complexity, right? So we want to define, well, let's keep it simple. Let's think about what do we mean when we want to define, when we want to say that, let's say I'm given a string and this string is completely random. Meaning what it means for a binary string to be random. And so there is this story that I guess at the bar it says, you were told at the conference bar that there was this guy here, Shaitan, defined a string to be random if it's its own shortest description. So let's think about it, right? So what would this even mean? Let's get a pen. So I'll give you a string and you tell me intuitively if this is random. Would this string be random to you? So why would this not be random? Yes, so let's not take this as a definition. Just intuitively think that this string is not random because there's some pattern that repeats, right? And how would I describe this mathematically? That, well, not mathematical, but in a different way, I might say 10, I don't know, 1, 2, 3, 10 to the power 4. So there's a shorter way to describe the string. And why would this imply that this is random? That means that there is an information there that can be somehow compressed. And the compressed information would say that something has to follow some logic that is compressed to this information, right? If you're able to compress the string so that you do not lose information that the string contains, like this writing here contains the same exact information as this one, but this one is much longer. For example, even if you think about this, right? This string doesn't seem random because you can write 0 to the power just following the same logic, 3, 6, 8, right? So somehow I'm able to say that 0 repeats 100 million times. This is a short way of saying 100 million zeros. So 100 million zeros do not really contain information that they specify because you can compress them. So intuitively, you might agree that I can call a string random if it is its own shortest description. Well, first of all, that we have to clarify what the description is, but just intuitively. So if you cannot make it shorter somehow, you can think of it even this way. So let's say you wrote down the string and there's no way to make it shorter, to describe it shorter than just writing it down. By the way, writing it down is also a description. Here is the string, right? And let's say you cannot make it shorter. That means that every bit string contains its own information somehow. So it's like independently contributing to the information of the string. So it's completely random, meaning every string is a new addition, right? So there's no logic behind how it's written that can be expressed in a shorter way. So this is, I try to describe it intuitively, but of course all of these things need definitions, and I will show you why. So to get the history right, it's not this person who actually defined it. This was kind of rediscovered in computer science, but before that, people were doing axiomatic approaches to probability theory, and the father of probability theory was Kolmogorov, and he discovered this beforehand, and then it was described by Solomonov, who I think was a student of Kolmogorov. So these things were discovered by mathematicians before they were adapted to computer science. So to get the history right. But first of all, we have to specify what is a description. Like my words description, it's something like this description, and I'll show you why specifying what is description kinda is crucial here. So here are some examples that we already talked about. If you have a string like this, intuitively it's not random right? It's not all zeros, there's no randomness basically. So you can describe it as 0 to the power 30, or maybe 0 and in parentheses you write 30 times. That's also some kind of description, whatever this means. And somehow the length of both of these descriptions, if you count characters, is shorter than the string itself. Somehow that means this string contains less information than they're specifying it. The same thing here. We see you can write it this way. But so information content, so I will call it complexity of string x. I will call it kx. What is kx? The idea is that kx would be the length of the shortest description of x. That would be the information content. Because even though you wrote a bunch of zeros, the information content is just 1 0 and how many times you wrote it. If you give me these 2 bits of information, what is written how many times, this kind of contains the whole thing. And this is what kx is supposed to capture. Complexity of x, or information content. What is the real relevant information that defines the string? And if I say that the real relevant information, that every constituent bit of my string contains relevant information, then intuitively this is completely random, meaning that old bits do not define new bits. So exactly, this discussion actually leads us to the point you have to specify mathematically what the description is to say that the shortest description is kx, or the random is when there is no shorter description. And if you do not do this, there are paradoxes. And here's the one paradox, which is here. So let y be lexicographically smallest string. That means the lexicographically shortest string, which cannot be described in 3 lines. This is a description of a string. Okay, maybe you will say we don't know what lines is, but let's say characters. So let y be a shortest string, so lexicographically smallest, the first string you encounter when you order them, such that it cannot be described in 52 characters. Right? This would be a description. This specifies a concrete string. Maybe you can think of it in a different way if it's harder to think about strings. Let x be a smallest natural number that cannot be described in 5 English words. Well, 5 is too small. Let n be the first natural number, or the smallest natural number that cannot be described in 50 English words. So you need 50 more words or more to describe this number. Maybe it's so big that you need 50 or more. But as soon as I said this, I described this number in less than 50 words. Because this description uniquely specifies the number. There's a unique number, so maybe there are many numbers that need more than 50 words of description, but there's the first one there. The same exact way, there may be many different strings that need more than 3 lines to describe them. However, there is the first one if you order them, and that one I just described in 1.5 line. So there's a paradox there. So you have to really specify what is a description in order to avoid things like self-referencing things like this. So this is a very careful thing to describe what is a description. And yeah, we just described y in 2 lines, and y is supposed to be the smallest string, the first string you encounter that cannot be described in more than 3 lines, and I described it in 2 lines, and that's a contradiction. So such thing cannot exist, and blah, blah, blah. So we have to really specify what is a description, right? And if you recall that we were in a theoretical computer class, we know how to treat description. So we have one candidate for the description. So a description of a string x will be u hashtag v, such that u is a string, v is a string. So the description of string x are 2 strings, u and v, such that mu, the Turing machine mu, started with v, prints x and halts. So if you think about it in meta world, the description of the string now is a program and an input. So when you run this program on this input, it prints your string. So somehow it's an algorithm to produce the string. You get the point, right? So description is basically an algorithm with an input such that when you give this algorithm this input, it produces your string. So something like this would also can be translated in these words, because it's an algorithm that writes 0 30 times. That this is just an algorithm that for human brain that writes 0 30 times. But of course we know that every algorithm is basically a Turing machine, so might as well say that it strings uv such that u, if you run u on v as a Turing machine, it produces x. And kx will be the smallest of such things. There may be many different algorithms that produce x, so there may be many different Turing machines and many different inputs, but the shortest one would be the description of x. Okay? There's nothing radical here if you think about it. Program and an input describe the output. So it's actually a very intuitive definition that this should be the description. But this is completely specified now. Now the question is, I do not want this hashtag here. I hate this hashtag. So I want this only consider strings. So, but now look, that position of hashtag contains information, meaning I have to know where the hashtag is. Because otherwise I have to know where to stop the machine and where to start the input. So I have to somehow encode this hashtag so that I'm able to guess where the hashtag is. And this is done by binary comma. U prime. So it's a self-delimiting string, they call it. Okay, what is this? Let's say I have a string. Let me enlarge this. Let's say I have string in zeros, ones, and hashtags. So it's some string that contains zeros, ones, and hashtags. So what does binary comma do? So it doubles zeros. So every time it looks at the string. Every time it sees zeros, it doubles. Every time it sees ones, it doubles ones. And hashtag, it's 1 0. Right? So if I have a string, I double zeros, I double ones, and every time I see hashtag, I go 1 0. And now, for every string I define, pay attention. For every string I define, u prime is I apply h to the length of u, right? Whatever, so if u is of length 20, so I write 20 in binary, I apply this process, I put hashtag in the end, and I just concatenate this with u. So let's write it, oops. And this is more efficient than just doubling everything. That's the whole idea. And so let's say my string is here. Let's follow the example 0 1, right? My string is 0 1, and I want to so I want to u prime this. So what does binary comma do to u? First of all, what is the length of u? The length of u is 2, right? So it's binary of 2. So it's length 2. So 2 in binary is 0 1. So what I have to do, I have to take, look here. I have to take h of binary of length of u. So basically what I have to apply h to 1 0. So h to 1 0 will take 1 1 0 0. It doubles 1 doubles 0. Then what I do, right, is I write 1 1 0 0. This is actually h of this length of u. Then comes hashtag. So instead of hashtag, I have to write 1 0. This is the code of hashtag. And then I just write u. So I write 0 1. So what this did, u was 0 1, and after coding u, so doing this u prime, would be 1 1 0 0 1 0 0 1. So why would somebody want to do it? Why would you want to do it? You think. So I'll show you in a minute, but first, how are we going to use this? Let's look at the lemma that this is really efficient. What is the length of u prime? I'm claiming that length of u prime is length of u plus O log of u. Right? This is more efficient than just doubling everything. See that, right? Because it's just length of u, not twice, but log of u. And why is this the case? Why? Because what is u prime? U prime is first, it doubles everything in u, but so it looks at the length of u in binary. What is length of u in binary? That's log of u. So length of u, if it's 17, log of 17 will be the length of it in binary. So this here is log of u. Then you're doubling everything. This is twice. So twice log of u plus 2 for hashtag, because hashtag was one symbol, now it's 1, 0. So it's 2 symbols, and plus whatever you wrote to u. So u just follows, it's concatenated in the end, so it's length of u. So in the end you get u plus log of u. So it's more efficient. And somehow, what is the idea? Why would you want to do this? And by the way, this is a very good exercise. I will put it up that you can define a binary comma, this coding procedure, which is actually more efficient than this. It's such that the length now is length of u plus log of u plus O log of u. So instead of O log of u with some constants here, you get just directly log of the length of u and plus O of log. And you can do this many times, by the way. So you can keep on applying this, nesting the binary things and get more and more efficient, but whatever. But now what I'm going to do, look, this is the whole point. This is why I defined this. Look, let me write down what I had before. So before I told you I take minimum of, I take program u, I write hashtag and I put input. And such that MUV, this is abuse of notation, but this means if I start MU on V, I halt with X. This is a horrible notation, but let's just, for simplicity, bear with me. But now I'm going to do this instead. Instead of writing U and a hashtag, I write U prime, right? And then V directly. How do I know where is the hashtag? So if I give you this, for example, I give you this. So before I had something like, let's look at this example again. So before I had, let's say, something like this. This was my Turing machine 1, 0. That makes no sense, but let's say it's a Turing machine. Well, it's a trivial Turing machine 1, 0. And let's say my input one was 1, 1, 0, 1. So this was my input. Now, this looks like this. So U prime is I have 1, 1, 0, 0, 1, 0, 0, 1, 1, 1, 0, 1. How would you know which one is the input? That is my question. How would you know here that where the input starts? Is that true? Is this here or is it here? But what if there, so look what's happening. Oh, exactly. Exactly. So you find a hashtag and whatever. So as you said, you find a hashtag and whatever you so you find a hashtag. So in this case, the hashtag is here, right? Oh, I cannot write. So hashtag is here, right? So what this means, this is just, if you remove the doubling, this is just 1, 0. All right, so this is 2. So you know that the length of u is 2. You know the hashtag is here. So the length of u is 2. So then this, you just measure 2. This is u, and this is your v. So somehow, knowing that you used binary comma, this completely encodes where the hashtag is, and it does it efficiently. Length of u plus log. So you do not have to, so it's more efficient than just doubling everything and doing things like this. Okay? So we will use this for binary comma. Next. Now lemma number 2 says that for any string, so let's see what it says and let's interpret this. It says that any string you give me, the complexity of the string, meaning the shortest description of the string, is shorter than the length of the string plus some constant. So up to some constant, this works as our intuition. Our intuition is like, okay, I can always specify a string by just writing it down. So if my string is of size 1 million, then there must exist a description which is shorter than 1 million. Because if I just write the string down, it has length 1 million, and it is the description of the string, so I wrote it down. And this is exactly what it said. The description of any string is shorter than the length of the string plus some constant. So at infinity, when you're dealing with very large strings, this kind of always stays the same. And this kind of, the idea is that you can always specify a string by just writing it down, or saying this is the string, and it's specified. And this is supposed to be like that. If this was not here, then it would completely be our intuition that the description is shorter than the string, but O1 is there. And how would I prove this to you? I have to give you a U and V such that this is actually a description. So let me show you. So let's describe. So I have to describe you a program that specifies X. So what is the program? MU is a Turing machine that just ignores whatever it is written on the, so it takes an input, ignores the input, and just halts. So it's just a trivial Turing machine that it has a transition function that it doesn't care what is written, it just halts. So this is my MU. There's a finite description of U, right? You can write this Turing machine down as an exercise that ignores the input at halts, just goes to an accepting state, and it will be a finite string, the description of this Turing machine. And now U prime X describes X. Why? Because, so U prime X describes X means that if I start MU on X, it outputs X. This is true because MU just ignores everything and stops, and it outputs whatever was the input. So this U prime X is the description of X. Okay? And U prime meaning I encoded U into so that I changed the hashtags. And what is the length of U prime of X? Length of U prime of X is length of X plus I just proved that U prime is of length O log of U here. I just proved that it's U, which is just a fixed number, 17, plus some log of U. So it's O log of U plus size of X. So it's X plus, I forgot here. So it's X plus O log of U plus O of U, which is this part here. Sorry, I misspoke. So you have this here. And now this is just a number. This is, again, just a fixed number. Because you can produce this Turing machine. It has just two states. And it's always the fixed number. Independent of the input, it always goes to the acceptor. So this is just a number. So it's X plus a number. So there exists a description, which is X plus some number. And of course, if there is a description that such that it's X plus some number, the minimum of all descriptions will be smaller than this. So the minimum of all descriptions has to be smaller than X plus O1. So this completely agrees with our intuition that you can just write down the string. But now you notice that this thing works with large strings. Somehow because what is this O1? This O1 is basically a description of the Turing machine that does nothing. And if it has, I don't know, if you write it in strings and it's size 16, then you really need to start work on large strings which are larger than 16 to kind of make sense of this. But anyways, what about this one? So what is the Kolmogorov complexity of 1 written n times? I'm claiming that to describe 1 written n times, I just need log n, and then just some number which I ignore in my head. So if you give me log n, this is the description, write 1 n times, because if I know log n, basically I know how many times to write 1. But strictly speaking, I have to give you a Turing machine, mu, which on some input prints n many ones. So I just trust you that you can construct a Turing machine that when I give an input, the binary representation of n. So let's say I want 1 to the power 17, so I give it 17 as binary. It reads it and prints that many ones. Then this Turing machine with the length of this input. Now think about it. Think about this. In this case, you didn't need to take an input because you're just writing the string down. You require no input. But in this case, you have to know how many ones to produce. So you have to know n. N is the valuable information. It is the only information encoded in this string, by the way. So you have to take an input. If I do not take an input, I will not be able to produce n many ones. So I have to take an input. This is actually crucial information. So you can produce a Turing machine. So your program is print once, but how many ones depended on the input. So it takes an input binary representation of n and then it prints 1. So the description is your program and an input. This describes 1 to the power n. What is the length of this? The length of this again is just log of n, and we already saw that this is just a fixed Turing machine. It has 01. Okay, this is again intuitively that specifying n many ones, it's really just specifying n. If you tell me n, that completely describes n many ones. Okay. Okay, so next, and now comes actually a crucial theorem, which is maybe, do such things even exist? So the question is, do random strings even exist? Meaning that if, did I define randomness? No, I have not defined randomness. Oh yeah, here's the definition of randomness, and here's the lemma that I'm mentioning. But so let's open up both of them. So I was running ahead of myself. So the idea is now that the string is random if it is its own shortest description. The same exact idea we had on slide 1. So the definition would be a string is random if the description of the string is bigger or equal to the length of x. Meaning, I know that the writing down the length of x is the description of the string. So the shortest description is this, actually, writing down the string. So mathematically, because of this O1s and everything's here, the string will be random if the description of the string is larger than the string itself, larger or equal to the string itself. And now I again come back to my question. The question is, do such strings even exist? Are there strings that are random, meaning that their description is larger or equal to this writing down the string? And we already had the hint that if this one thing should be random. But I'm claiming the following. For any n, there are random strings. Any n you give me, there must be, so let's say n5, there must be a string of length 5 which is completely random, meaning there must be a string of length 5 such a description of the string cannot be shorter than 5. You need all 5 bits. And the proof is ingenious. I assume the contrary. Assume that for all x, so I fix some n. So you give me number n, and I want to prove that there exists a random string. So there exists a string such that the description of the string is larger than x. So I assume for some string x, like for all strings x, the description of the string is shorter or equal to n minus 1. So what is the length of x? So it's bad that I have to zoom out every time. But if x is in Bn, the length of x is n, right? So it's the length of the string. And I want to prove that there exists such things that the description is bigger than n. So what I want to prove is that there exists x such that k of x is bigger than n. So n is the length of x, so the description should be bigger or equal to n. Then the string will be random, because you cannot make it shorter than n. That means any description is at least n. And let's say this is not true. That means that for all things, there does not exist such thing. That means for every string, the description is less or equal to n minus 1. Let's assume this. So now, let n be a number. So it's the number of all possible descriptions which are shorter than n minus 1. So it's, what is this? So this is u prime v, whatever u prime is, whatever v is. So u is a program, v is an input. Let's say this is some program, some input, very general. But let's say this is shorter than n minus 1. Right? So I assume that these descriptions are n minus 1. I also assume that for each x, the description is shorter than n. Let's say this is better worded. Shorter than n. So that means less or equal to n minus 1. Then let's look at all possible strings that are shorter than n. How many are there? How many strings are there that are shorter than n? Can you count? How many strings are there of length 1? Yeah, there are 2 strings of length 1. How many strings are there of length 2? 4. How many strings of length 3? 8. And you go up all the way up to whatever, 2 to the power n minus 1, right? This is how many strings are there of length n minus 1. So there cannot be more descriptions than there's strings in total, right? I just wrote down all possible strings, so all possible descriptions that are shorter than n are also here. Okay? This is what is written here. So this is exactly what we wrote. It's how many strings of length 0, how many strings of length 1, length 2, length 3, up to n minus 1. So this is just number of strings of length I. I goes from 0 to n minus 1. And this is just a geometric progression. Yeah, we forgot strings of length 0, which is just 1. 1 plus 2 plus 4 plus 8. And this geometric progression, you can write down the formula from your high school, is 2 to the power n minus 1. But how many strings are there in Bn? So the question, how many strings like this are there? 2 to the power n, right? So there are 2 to the power n strings, but there are only 2 to the power n minus 1 possible strings that are 1 shorter. So not all descriptions can be shorter. There is at least, by pigeonhole principle, there is at least 1 string that does not correspond to a description here. So there has to be at least 1 string that has a longer description than n minus 1. So for any n, there are just not enough short descriptions. That's the argument. So there has to be a string that cannot be described by, because every description uniquely determines a string. How? That description means that you have program input and it outputs a string. So there must be a string that is not here, that is not described by something shorter. So there are not enough short descriptions, basically. That's actually a very good philosophical way to view this, that you said there is no logic. So randomness means that there is completely no logic in writing down the string. Every bit is somehow important. If you remove any of the bits, all the other ones do not determine this bit. So it's completely random. So it contains all the information. So every bit is a constituent of the information. And if you think about it, having all the information means you have no information. So if you have complete fuzziness, that means you basically have no information. So your complete randomness can be viewed as, I'm being philosophical, so complete randomness can be viewed as containing all the information, but somehow also containing none of the information. It's like the things when they say that pi contains every single poem ever written or whatever. That is because pi, if this were true, we do not know this, But if this is true, that would mean that pi is completely random and it contains everything. So it contains basically, it makes no sense to talk about it containing some bits of logical information in there. This is exactly what it says. But this is all just philosophy. We just go back to mathematics. So we know that random strings exist. For any n, random strings exist. And now let's just focus on one thing, why Turing machines? What I'm going to show you now, it doesn't really matter. Any model you choose for your computation, if it's a complete model, be it C machines, Turing machines, something else that is also complete in a sense that it describes mu recursive functions or whatever. So any other computation model will give you the same definition. So what I mean by this is, let me just tell you. So definition of Kx really depends on coding of a one-tape Turing machine, right? Our definition really used that we're using Turing machines for describing our programs and that we're coding it with binary or whatever. So it's a Turing machine's MU. So what we really define, it's not Kx, but we define K one-tape Turing machine X. So it really depends on Turing machines, but I'm going to show you that it doesn't really matter. What if we use another, like C programs, instead to define KCX, or maybe Python, or whatever, or C#. So these are the codes that I'm looking at and not Turing machines. So what if in general we compare Kmx and Km'(x) for arbitrary machine models M and M'? Instead of using Turing machines, we use something else. But we assume that each one of is capable to compute the computable functions. So it's a complete model. It's not stupid. So it can, everything that can be computed by computable function, we mean this mu recursive things, it can be computed by this machine. The first and the most famous candidate is Turing machine, but there are others. What we can prove from this by writing an interpreter is that Kolmogorov complexity of string X differs for different models of computation only by an additive constant. So if you use something else, let's say you use Turing machines and something else, and you compute Kolmogorov complexity using Turing machines and something else, I mean, you can make the first part of your description shorter maybe by describing not Turing machines, but something more efficient. However, whatever you do, they will only differ by a constant. So if you disregard constants in general, the Kolmogorov complexity does not really depend on the fact that we're using Turing machines. And how does this work? You have to write the interpreter. So it's a break time, so let me just quickly say this and I'll leave it in the recording and as your exercise. So if you assume that uv prime, the shortest description of X in model M, let's say for Turing machines it's u prime v, and let's say J is an interpreter of programs from M for M written in M prime, meaning it, i.e. if J starts with A prime B, it simulates program A on input B. And by Church's thesis, if both of them computable of both programs are complete in the sense that they compute all the computable functions, then it's possible to interpret one into another. So you can translate Turing machines into Python code. And you can take Python code and translate it into Turing machines. If Python is complete, meaning it's a complete language. And J would be that interpreter that interprets programs written in M into M prime. And then J u prime v is the shortest description of X in a different model, because if u prime v is the shortest description in M, then you apply J and then it translates. And then Kolmogorov complexity in M prime of X will be u prime v applied J of this, and of course J is a finite length, it's u prime v, and u prime v is Kolmogorov of X in machine M. So really you just get this additive constant comes from translating from one language to another. There's nothing fancy here. Okay, let's take a break now. Okay, we continue now. So now comes another crucial lever, that Kolmogorov complexity is a not computable function. That means that given a string, you cannot compute its algorithmically compute its Kolmogorov complexity. Cannot tell what is the shortest possible description of the string, unfortunately. Why is that the case? Why is kx not computable? Let's assume kx is computable, right? So let's say there exists an algorithm, that means Turing machine, that computes kx. Now let's construct another Turing machine then. Let's construct this Turing machine mu. I will describe this so it completely specifies u. So mu starts with an binary length of n. So it starts with input n written in binary. So then it enumerates all possible strings so let's say in lexicographic order, so it of length n. So it looks at all strings of length n, 0, 0, 0, 0, 0, 0, 0, 0, 1, and so on. So lexicographically, at all strings, and it computes kx. So if kx is computable, then I can compute kx with something. So I enumerate all strings, I compute kx, and once I find a string such that the description of x is longer than n, I output this string and halt. This string must exist. This means that this string is random. So once I find the random string, I output the strings, and this must happen because I just proved that there exists random strings for any n. So this does happen. So now I start enumerating all strings of length n, and as soon as I will find, and I compute kx, and as soon as I find the random strings, because I can compute kx, I know it's random, I output and I halt. Now, this Turing machine u with input n describes this random string. Why? Because it takes input n in binary and it outputs x. So it's the description of x, and x is random. So this means the description of x has to be bigger than n because x is random. So, well, k of x has to be bigger than n because x is random. Now, k of x is the smallest possible description of x, which is bigger than n by x being random. And if it's smallest possible description, it must be smaller than whatever I described here. So u prime binary n. But what is the u prime binary n? It's length of u, whatever O1 this is, it's a fixed Turing machine, plus log of n. And I just got proved that log of n plus a constant is bigger than n. This cannot happen. So such Turing machine cannot exist. That means I cannot compute kx. There does not exist an algorithm that for x computes kx. So you cannot algorithmically compute the length of the shortest possible description. If you could, then you could do this, and then you would prove that log n is bigger than n. Stringips. Moments. Okay, the next topic is conditional Kolmogorov complexity. So the question here is, how much does a given string help to describe another string? So let me give you an example. Or should we? For example, instead of looking at the definition, let's look at let me actually write so here, let me write it down. So let's say, what is x? So let's say x is 1, 0, 0, 1, 0. By x bar, I mean I just flip once as 0. So I write 0, 1, 1, 0, 1. So this is the same as x, but zeros and ones flipped. Now I give you a question. I ask you a question. What is the complexity of this if I tell you x bar? So before so what would be the description of this thing, right? So description of this thing with the shortest program with some that on input gives you this, but I want to in addition give you this. So you have to give me a program that a description is like a program which takes an input and outputs x, but in addition I tell you that x bar is this, then you do not really need anything. So if I tell you this, you just have to flip everything and you know x. Somehow telling you x bar completely specifies x. So that is the conditional Kolmogorov complexity. What is the description of x if I already told you y? So for the definition, that would, so I want to define Kolmogorov kxy. So y is given, and what is the description of x of is y given? Intuitively, if x bar is given, description of x should be just a constant. It should not really depend on the length of x if x bar I know. That is the intuition. So kx given y is, I have two strings. It's the smallest description again of u prime v, but now mu started with v and also knows y. So your program takes v as an input, but also separated by hashtag somehow knows y. So it can always use information from y and an input to output x. So if your Turing machine takes an something input, it's supposed to output this, but it also knows x bar. So it kind of doesn't need any other inputs than this one, and it just does this. And so according to our intuition, this is indeed true, that if x bar is given, the description of x is just a finite O1. So we always treat these finite things as being 0. So it's like, it's already described. If you have x bar, x is already described, independent of how long x is. Why? I have to produce u prime v. Just pay close attention. It might be confusing what is happening here, that mu is only starting on v. Mu is starting on v hashtag y, but I'm calculating the length of only v. So I take into account in my description the length of v and not length of y. Length of y is somehow always known. So in this case, I will construct a Turing machine that just, so what is this supposed to do? So mu now has to start on, so I will start it on nothing, basically hashtag x bar. So I do not really have to take an input, and the description of this thing is u prime and then epsilon, because I do not care about the x when I describe the description. So the description of this machine is just O of, so it's just a, so this is just some number m, because it's just the length of u prime. So mu started with nothing hashtag x, just flips all bits of y and halts. Then in my definition of description, u hashtag x describes x, and in Kolmogorov complexity only u prime, the length of u prime goes in, because this was given without the input somehow. It doesn't count as an input. Yeah, yeah, that's actually a good way to, it's like built into your machine. So this y is built into your hard disk, so when you're calculating how long the description has to be, you do not count for y. But now if x bar is built in, you do not care, you only need empty things as an input, and you know x. And now the lemma is that the substrings of random strings are almost random. What this means, this is actually very intuitive also, so maybe it's easier to understand mathematics. Let's say I'm given a string that has 3 parts, x1, x2, x3. So these are 3 parts of my string. And let's say my string is random. So I give you a random string and I take 3 parts. The question is, are those parts also random? Are bits of random string random? Intuitively, they should be. If the whole thing is random, if I cut out the piece, that piece should also be random. Because if you can make this piece shorter, then it makes the whole thing shorter. So this is exactly but now we give even farther. So it's not that I'm just cutting out the piece. I'm cutting out the piece and I'm telling you I give you x1 and x3. So I look at my string, I cut it in 3 parts, and I'm telling you what is the description of the middle one if I give you x1 and x3. Somehow giving you x1 and x3 should not affect the description of x2. That's the point. And what this says, that this is almost the case, meaning that the length of the description of the middle part, given the left part and the right part, is longer than the middle part. If without log n, that would mean that the middle part is completely random. But given the middle part, that you now already have the information that if the string was length n, you subtracted something. That's already, intuitively, you have some information on the length, the boundary of the length of the middle part. Maybe philosophically, but mathematically, this is description of x2 given x1 and x3 is longer than x2 minus log of n. So up to log of n, this is like random. We'll see. It comes from the proof. So where does the log n come from? So let's say u prime z is the shortest description of x2 given x1 and x3. So let's say it's, I do not know what machine mu is and what the input z is, but such thing exists. And so let's say it's the shortest description of x2 when I'm given x1 and x3. This means that if I start my machine mu with input z, and somehow, as you said, x1, x3 is also given, it's built into my machine like this, then it must print x2 and halt. Or in other words, x2 and x1, x3 given, x2 is the length u prime z. Because u prime z is the shortest description. Now, let's design a new machine. Actually, let's open everything up so we can see, scroll through. Let's build a new machine now. This new machine starts with input u prime z. So it takes the same input as this guy. It takes this guy completely as an input, u prime z. So it takes the machine and z. But it also knows the binary length of x1. So it takes an input binary x1, comma, meaning I want to make it as short as possible, x1 and x3. So it knows the length of x1, somehow it knows x1, x3, and this guy. So this is just and what does it do? First, it generates z hashtag x1, x3. So it just unpacks, removes the comma, writes z, then hashtag. It knows x1, x3. It can generate x1, x3. Then it simulates mu with this input. So if you simulate mu with this input, you will print x2. So it will print x2, and then what this will do, it will insert x1 to obtain x1, x2, x3. But it has to know the length of x1 in order to do this. You think about it, why? It's actually a good exercise to think about why did I need the length of x1 to do this, to kind of differentiate what is happening here. But anyways, so it outputs x2 and then it obtains x1, x2, x3. So basically, it's a description of x. V outputs x by doing all the things I described. If it outputs x, remember, x was random. So the description of x1, x2, x3 is bigger than n. Now, description is the smallest possible thing that outputs x, so it has to be smaller than description of this whole thing, meaning v prime, because I use v prime, and input u prime, z prime, binary x, length of x1, x1, x3. The length of this one has to be bigger than the smallest possible description, and now I just do mathematics. Now, vu prime is just some fixed Turing machine, so it's some number, plus, v is some number here, so v goes into number 01. uz prime is exactly the length of uz prime is k x2, x1, x3, as we said before. So you get k x1, x2, x3 for uz prime. Now, for binary length of x1 is shorter than x has length n, so it's O of log of n. This is actually a crucial point now. This is where the log n comes from, because you need to know the binary length of x1 in order to put x1 behind x2, x3. Somehow you should be able to differentiate when x1 stops here and x3 begins, so you have to know the length of x1. That's where the log n comes from. And then you have x1, x3. And you just n minus, so here you have n is less or equal to some number plus this guy plus O log n plus this. Now this, put it to the left side, so n minus x1, x3, if you put this part to the left, is x2. So you will get, if you pull this one left, you will get x2 here, and you put log to the left as well, you get x2 minus log is bigger than k x2, x1, x3. So if x1 and x3 are given, the complexity of x2 is bigger than x2 minus log of n, where actually log of n came from the fact that you have to know length of x1. And as I said, it's a good exercise to think why this is the case. It's just easy, but you just have to think about it. Okay, so you're getting confused. Let's continue. And let's do crossing sequences. This is actually a very... Let me tell you where we're going. Will this turn off if I turn it off? Remember in deterministic complexity classes, here in the last lecture, somewhere, where was this? Where we had the example when something was on one tape we needed square amount of time, and in two tapes we needed, oh, here. Remember this language? This language here. So string x, n many x's and a string, and we said that on two tapes you can just copy it on the second tape and accept it in linear type, but on one tape you have to go back and forth, and you need square amount of time. Where we're going now is that I'm gonna prove that this language, just written in a different notation, so this is the same language, but instead of x's I have hashtags now, and instead of string, m many hashtags and a string, so it's the same exact language, but the notation is different. Instead of x's I have hashtags. I will prove to you now that this language, and if you have a Turing machine, which is some Tn time-bounded one-tape Turing machine, and this Tn is grows slower than n squared, so let's say it's linear, then m does not accept this language. So I will prove to you that that language that we described, that you need a square amount of time on one-tape Turing machine, cannot be accepted in linear time, for example. Cannot be accepted with anything less than square amount of time. And this is actually one of the very few lower bound proved in complexity theory. Complexity theory has easier time proving upper bounds, but not lower bounds. So lower bound is something like, this cannot be done faster than this. This is a lower bound. But the upper bound is the other way around. So when you know that, the upper bound. So, but before we get to that, we have to describe what is a crossing sequence, and this is actually a very, it seems easy now, but it's actually a deep philosophical observation. Not philosophical, but it's a deep observation that if you have a one-tape Turing machine, so that is Z, so blah, 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 and without loss of generality, we assume that the computation of M ends with the head on the left of the tape inscription. That means when computation ends, I just add another state and it goes left. So I always assume that it always ends to the left of whatever it writes on the tape. When it's finished, it goes left. What is the crossing sequence? And I'll tell you what is the deep observation after this. Given a string and a number of tape cells I, so maybe I should draw it. So you're given a string So this, let's say it's A, B, C, A. So there's some string written, and there's just a tape cell number I. So let's number the tape cells. So it's tape 1, cell 2, cell 3, 4, 5, and 6. So I just number my cells, and I give you cell, let's say 3. So I give you this word A, B, C, A. So I give you this word W, and I give you 3. So it's W and tape cell I of tape cells. The crossing sequence, what is crossing sequence A, B, C, A, 3. So this is the sequence of states of the Turing machine started with W. So you started my machine on this W, and it's the sequence of states which I record as the head crosses the border between tapes I and I plus 1. So I in my case is 3, I plus 1 is 4. So this is the border between 3 and 4. So I watch my Turing machine. It starts here. It goes, maybe it moves like this, goes back and forth. And when it crosses this threshold, I record the state, let's say Z5. Then maybe it operates here again, and crosses it again. I record it maybe Z17. Then it operates here, crosses it again. I record the state Z8. And I assume it always ends on the left, so it operates, it crosses it again, and it's finished somewhere. So maybe it's Z11. So the crossing sequence 3 will be just recording the states when it crosses this threshold between 3 and 4 on this input. Okay? And the deep observation I mentioned is that Turing machines are exactly, everything computable is computable by a Turing machine, right? So it's just general definition of an algorithm is a Turing machine. And what it's really doing, it is a completely dumb machine that what is the information that it transports when it moves from here to here, let's say? The only information it transports and remembers is a state. So it's completely irrelevant in some sense that, so I'll show you the proof now and you'll see what I mean, but this is the observation that all our computation is, in general, all the algorithm is just making steps, and at every step, all the information I keep is kept in some finite set of states. So what this means is the following, and maybe this actually giving you this lemma mathematically the proof is actually just pictures, and I'll show you why. But what does this say mathematically? It's in large. So what does it say mathematically? Mathematically, this thing says, so I have u, v, x, and y are some strings in my alphabet. And I assume that u, v, and wx produce the same exact crossing sequence between them. So what exactly this means, unfortunately, I have to zoom out now. So I have u. So let's call this, so let's say this string completely. So this string is ux, and let's say I have another string, which is a different length maybe. So this string is uv. So here I have u, and this guy also begins with u. So it has u and x, and this has u and v. And I also assume that if I so uv and wx, sorry. So yeah, let's write it, let's call this guy w for the picture. So it's w. So I have two strings, wx and uv, whatever. And what I say is that if I look at the string uv, and I look at the string wx, and I look at this threshold here, and this threshold here. So this threshold that is right after the length of w and length of u. So this threshold here. And let's say I assume that the crossing sequence, meaning the states that this thing is crossing and this thing is crossing, is exactly the same. That means when I record the states that this my machine is crossing Wx, let's say I get Z5, Z6, Z7, Z11, and I get the same exact Z5, Z6, Z7, Z11. Let's say they are exactly the same. What I mean, what this lemma is claiming now is that if I cut out W and glue in U here, this will be accepted if and only if this thing is accepted. Can you justify why would this be the case? The idea is this, that doesn't really matter that there is a W here. The information that this guy is transporting from X is exactly the same that this guy is transporting from V. So if I replace V with U, exactly the same thing will happen as it happens on this side. So it will exactly do the same thing as it did here. So it will accept UX if and only if it accepts UV. So if it just transported the same information from left to right, it will do the same thing. It doesn't remember anything else from the right side. It doesn't care if it was X or V on the right side. If it transports the same information after this threshold, if I replace this threshold with something else, it just keeps doing the same thing. Let's actually look at the pictures. The proof is just pictures here. Here are the pictures that it's like a surgery. So this is, let's say, as I drew U and V, and let's say this is my Turing machine and time is this way. So my y-axis is time. So time goes, so this Turing machine comes this way. It crosses to V in state Z1. Then it comes back in state Z2, goes to Z3, then does something, movements like this here, and goes to Z4. Now let's look at WX. In WX, maybe it does something, U is not the same as W. So you see, it does something different here. So it goes this way, maybe it does something completely different than here, goes like this, here it just goes directly. But whenever it crosses in state Z1, maybe on X side, again, it does completely different things than on V side here, blah, 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 blah. But at the crossing, it's Z2 again, Z3 and Z4. So this state Z1, Z2, Z3, Z4 is exactly this here. So now what I can do is I can erase U here and glue it, or maybe I can do it the both way around. Which one is here? Here's a nice picture. So what I can do is I can take this part and glue it to this part. So I do a surgery, like I remove this left side of this thing. Actually, I can actually do it live and you'll see what I mean. This is actually a good idea. If, no. Keep. Oh. It's recording. Oh, it's still recording. We're live. Very good. So if I do a screen snip now, and I'll show you what I mean. This is the last lecture. Let's relax a little bit. I might actually record one more lecture from the comfort of my own home, just for completeness, but that will not go into the exam. But if you go here, let's enlarge this. Cooperate. Yeah, here. So I hope the scissors, oops. Where is lasso? I hope this works here. So this completely failed. But what I mean is, if I cut this out, this here completely, and I glue this here, imagine taking this out and putting this here. You see that you will exactly coincide with the crossings will still be the same, Z1, Z2, Z3, Z4. Right? So if you cut this out and glue this here, you will get this. There will be exact coincidence at the crossings. And your machine would do exactly the same on the left side as it was doing here, not caring what is happening on the right side. It will do exactly the same on the right side as it did here. So your machine will basically do left. Why doesn't this work? It will do left side from this one, and it will work as right side on this one. And in amalgamation, it will accept if and only if this thing accepted. Because it's just repeating whatever this thing is doing. So at the exact moment that it moved, only thing it took with it is the state. So it read something, overwrote it or whatever, and moved. This is the time I recorded it. When it already moved, I do not care what it did 10 days ago or 10 movements ago. The only thing that is now it took from the past is the state. And now if it's in the state, so let's say it's doing, let's say W, so it's moving, and it moved in Z1. Right? If I glue instead of X, if I glue V, it will exactly behave like Z1 reading V. It will not care what happened in the past because it only has its state. So exactly at the moment where the crossing states are the same, you can remove the whole part and glue in the other part, and the same thing will happen. The thing will accept if and only if it accepted before. So exactly, mathematically speaking, X will be accepted, meaning you glued X will be accepted if you glue X, if and only if U and V accepted to begin with. If U and V accepted and you remove V and glue in X, it will still accept. Because the crossing sequence is the same. So if you identify a place in your string where the crossing sequences are the same, maybe here, which are not exact, they do not exactly line up, you can remove this part and glue it here and it will still accept. ერთი და იგივე crossing sequence-ები უნდა გქონდეთ. დელტები კაკრას რო არა. And that is actually a crucial idea to prove our lower bound theorem. And I'm not going to enlarge the whole screen, so I'm scared to lose the recording. And this is the lower bound that I advertised, that it's exactly the same language as we had here. Here, instead of X, if you write hashtag, and instead of W, if you use U, this is exactly that. That you write U, hashtag U. And I'm saying that if this language is accepted by some time-bounded one-tape Turing machine, then that time bound is smaller than n squared. Oh, if m is, it's bigger than n squared. So in other words, what this says that if you have a Turing machine, one-tape time-bounded Turing machine, which has time bound smaller than n squared, then it cannot accept this language. That means if it's accepted, it has to be bigger than n squared time. So for example, you can never accept this language in linear time. So this square amount of time you need to go back and forth is unavoidable. This is basically what this proves. აიხა უნდა დავამტკიცოთ, არა, ეგრე არაფერ, აიხა აი ეს არის. არა, მაგას გამოვიყენებთ. We will use what we said before for this. What I'm going to do is I'm going to cut this and see. It's actually an ingenious proof. I can zoom it this way when I do not have full screen. So first of all, assume such thing exists. So assume I have a Turing machine which works in less time than n squared, and let's assume it accepts my language. So assume M is machine that operates in less than n squared time, and let's assume it accepts L. Now I take one string, so string of zeros and ones, then M many hashtags and the U again, and I take another string, so other string, M many hashtags and U1, such that they're not equal. So what I mean this, so for example, if I take 010 hashtag 010, right? And I take something else, 001 hashtag 001. Both of the strings are in this language, right? String, the hashtags as many as the strings, and the string repeats. So both of these are in this language. Both of the strings are in the language. But now I claim that your machine has to accept both of them. It has to tell you yes on both of them. But I'm claiming that the crossing sequences have to differ. So what I'm claiming here is pick an I between, in this case, in our case, M is 3. In my example, M is just the length of this guy. So I pick an I between 3 and 6. That means I pick an I here or here, basically. So somewhere in between hashtags. So I'm somewhere in between hashtags, between 3 and 6. So 1, 2, 3, whatever, here, 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 or here. So I'm operating on hashtags, and I'm claiming that the crossing sequence between this guy here, 101 hashtag, if I start my machine on this input, and let's say my I is this guy, which is 1, 2, 3, 4. So my I is 4, does not equal to a crossing sequence of 001 hashtag, whatever my machine is. Why is this the case? Why they cannot be equal? Because if they were equal, by the lemma I just proved, I could glue them together. That would mean that და რახან crossing sequence-ები იგივე აქვთ, უნდა დააექსეპტოს შენმა მანქანამ, იმიტომ რომ მეტი არაფერი არ გადააქვს იქით. So if they were 101 hashtag, then I could glue these guys together and I would get something like this. If I glue them here, if the crossing sequence is whatever this crossing sequence is here, ZK, let's say. So whatever this crossing sequence is here, if they are the same, whenever I'm crossing, I can just remove this guy, substitute the other guy, and if the before guy accepted, and I know that the before it accepted before removing, this one has to accept, but this one is not in the language because the different strings. So crossing sequences have to differ. This is the main idea of this proof. Everything else is just mathematics. So what the idea is here is, I will go fast since we are running out of time, and so we describe the main ideas that the crossing sequences have to differ. So what I do is I code my crossing sequences in binary again. What is a crossing sequence? It's just sequence of strings, so sequence of states, right? So I want to turn it into binary. So the code is, I want for it to be a binary string, and I trust that you can do this because there's z many strings, and if you can think in your head how to code something like this, z17, z12, z3, z4. Let's say you have this crossing sequence like this. You want to code it in binary. You have to turn these numbers into binary and blah, blah, blah. And it, depending on how many states you have, when you code, you will be proportional to the number of states in log because you're doing it in binary. So if there are 37 states and you're writing them in binary, the code will be, row would be log base 2 of 37, whatever this number is, and that is the length of 37 in binary, and it will be proportional to that. So it will be the code of the crossing sequence, this, it's not quite binary comma, it's like this, will be the length of this guy will be proportional to whatever this length of row is, depending on how many states you have, times whatever the crossing sequence you're coding. But I trust that you can do this. It's not even specified. And now I'm gonna give you a description of a crossing sequence. So I will describe you the string U by a crossing sequence. How? Let me just say this and we finished. Oops, we have 2 minutes only. So how do I describe U by a crossing sequence? So I'm telling you that if you give me a crossing sequence, so if you tell me on a hashtag what are the crossing, I will tell you exactly what U is. How? I describe you a Turing machine. I describe to you the Turing machine that starts with input. It knows the length M. So it knows the length M. It knows I, meaning where the crossing sequence line is happening. So in our example, we had 4. And it knows the crossing sequence. Then it can print U. How would I print U? I will enumerate all possible U. And for each U, I will run my machine M with input U, hashtag U, and see if the crossing sequence at position I is exactly whatever was in my input. If it's different, then it's not U. Because all of them, I just showed you that all of them have to have different crossing sequences. The only time I will find this crossing sequence in point I is exactly when I find U. So if you give me the point, and you give me the crossing sequence, it completely determines U. Because every U has to have a different crossing sequence at this point. That's the whole point here. So then MV started with M, I, the place, and the crossing sequence of this guy detects this crossing sequence for U and only for U. So it outputs U and holds. So now crossing sequences completely determine the strings here, because every string must have a different crossing sequence. And only thing left is to do this analysis, and I will just, since our time is up, I will just very quickly go through it, and you can look at it in the recording that now this guy, so this machine is a description of U. So what is this machine? V is the code of the machine. Then as an input takes binary M, it takes it knows length M, it knows the position, and it knows the crossing sequence. This is a description of U. Random U exists. So let's take this random U. For any M, random U exists. If your string is random, then KU has to be bigger than M, because this is the definition of a random string. Now KU is a description of U. This is also the description of U. KU is the smallest description, so KU has to be smaller than this. Now I'm doing mathematics on this. What is V? What is V? It's just some number. What is binary M? The length of binary M, it's log of M. What is the length of this guy? It's row times, remember the coding I did here and I said it's proportional. So it's row times the length of the crossing sequence. Right? Where did I go? So I is less than M, right? So it goes into O log of M. Is I less than M? Yeah, I is between M and 2M, so it can be swallowed in the log of M. So what this says, if you rearrange the terms, it says that length of the crossing sequence at I is bigger than M minus log of M divided by rho. And that is log of n. This means that when m is bigger than m0, for some m0, you can substitute m divided by 2 rho here. Why is this the case? Because m minus log of m is always bigger than m divided by 2 for some m, and you substitute this here and you get m divided by 2 rho. And finally, I just do not have enough time. The runtime is at least sum of lengths of crossing sequences, because the runtime is how many steps your machine is making, and the crossing sequence is just counting the states. So if you sum up all the possible crossing sequences, the runtime has to be at least that. And if we set n equals 3m, and the runtime, you do the analysis, You just take only from m to 2m, sorry I do not have enough time, and you plug this one here, and you will get that the runtime is bigger than n squared divided by something, so it's O(n) squared. So it cannot be done in a linear time, no matter what you did. So sorry I had to hurry here, but we have to finish because I also have to go, unfortunately. But yeah, you should be able to, I went too fast here, but you should be able to deduce something. And this will also go into exam. And I might record one more lecture at some point, but that one lecture about P and stuff, P equals NP and stuff, will be just for leisure. It will not go into exam. So exam will include Kolmogorov complexity.